Hello everyone, this is Rashika Janjala. I'm an educator at Unacademy. You can follow me on Unacademy Learning where you can find my other courses as well. In this lecture, we are going to discuss about the design of helical springs under fluctuating loadings. So now we are going to see how to design helical springs that can resist the fluctuating or the variable loading acting on them. Okay, and please rate, review, and share the video, and also subscribe to Unacademy YouTube channel.
Welcome again to Design of Helical Springs against fluctuating loads. In many applications, the force acting on the spring is not constant, but varies in magnitude with time. For example, the valve spring of an automobile engine is subject to millions of stress cycles during its service. The springs subjected to fluctuating stresses are designed on the basis of two criteria, design for infinite life and the design for the finite life. I have discussed about these two terms, the infinite life and the finite life, in the discussion on the design of machine elements against the fatigue failure, right? And let us consider a spring subject to an external fluctuating force which changes its magnitude from P maximum to P minimum in the load cycle. Okay, so we have the fluctuating load having the maximum value P maximum and the minimum value P minimum. Okay, the mean force Pm and the force amplitude Pa are given by the two equations here. Pm equals to P maximum plus P minimum by 2 and Pa equals to P maximum minus P minimum by 2. So the mean stress is calculated from the mean force by using shear stress correction factor Ks, and it is given by term equals to Ks into 8 pmd by pi d cube. So we have found the relation for the total shear stress developed in the spring wire given by tau equals to K into 8 pm pd by pi d cube, right? So here we are calculating the mean stress for the spring or the under the fluctuating loadings given by tau m equals to Ks into 8 pmd by pi d cube. Here we have included Ks, which is the stress concentration factor, and we haven't included the curvature correction factor because the effect of the curvature on the mean stress developed in the spring is negligible. That's why we haven't included the curvature correction factor for the mean stress calculation. Okay, so the stress correction factor is given by K is equals to 1 plus 0.5 by C. Okay, so we have these two values for the calculation of tau m, which is the mean stress developed in the spring which is under the action of fluctuating loadings. Okay, for torsional stress amplitude, it is necessary to also consider the effect of stress concentration due to curvature in addition to direct shear stress. Okay, so the effect of curvature on the stress amplitude is considerable. That's why we have to include, or we have to add the curvature correction factor in the calculation of the stress amplitude given by tau a equals to Ks into Kc 8 pad by pi d cube. As you can observe here, we have another correction factor here, which is the curvature correction factor given by Kc here. Okay, and the product of K is the stress concentration factor, and also the curvature correction factor is given by K, which is called as wall factor. So we have discussed about this wall factor in the past few lectures, right? So we have found the value of the stress amplitude for the spring under the fluctuating loadings given by tau a equals to K into 8 pad by pi d cube. So we have these two terms, tau a and tau m. So now with the help of the fatigue failure theories, we are going to find the safe values of tau a and tau m for the safe design of the spring under fluctuating loads. Okay, so in general, the spring wires are subjected to pulsating shear stresses, right, which may vary from 0 to S-SE, where S-SE is the endurance limit in the shear for the stress variation from 0 to maximum value. And the data regarding the experimental values of endurance strength of spring wires is not readily available. That's why we have some scientific data or the relations between the endurance limit and the ultimate strength and the yield strength, the shear yield strength of the material and the ultimate strength of the material given for patented and cooled down steel wires. We have S-SE equals to 0.21 SUT and S-SY equals to 0.42 SUT. So if we have a spring which is made of patented and cold down steel wires, we can use these two relations for S-SE and S-SY. So with the help of these two relations, you can find the relation between S-SE and the S dash sy, which is the shear yield strength of the material. Okay. Similarly, if we have a spring which is made of oil hardened and tampered steel wires, we can use the relations S dash se equals to 0.22 SUT and S dash sy equals to 0.45 SUT. Here in these relations you can find SUT is the ultimate strength of the material. So now we have found the value for the tau A and tau M. So with the help of the data or the theories of failure, we can find the safe values of tau A, the stress amplitude, and tau M, which is the mean stress of the springs under the fluctuating loadings. Okay, here you can see in this figure, we have a plot against tau A against tau M, which is given here in this figure. You can find the line of failure. Here you can see AB is the line of failure, which is plotted from the data that was obtained from the experiment, right? So this line AB represents the stress values at which the failures occurs in the mechanical elements. And here you can see another line which is CD, which is called as a design line, which is obtained from AB, the line of failure, by including the factor of safety. Okay, so the CD is obtained by dividing every point on AB with factor of safety. Okay, and it is parallel to AB. So we have a load line which is obtained by pointing the stress values of the variable loading acting on the spring. Okay, so the intersection of this, the load line and the design line, gives us the safe values or the permissible shear values for the spring under fluctuating loadings. Okay, so here you can see we have the desired values or the permissible shear values for this spring. We have tau A and tau M for the intersection between the load line and the design line CD. Okay, so see here, as you can observe, we have the triangle ABE and another triangle XFT. So as you can observe from this figure, you can see the height of this AEB triangle is S dash E by 2 and the base of this triangle is S dash SSY minus S dash E by 2. Okay, and for this triangle XFD, we have the height given by tau A and the width here in the base we have SSY by FS minus tau N. Okay, so we have these two, the height and the base for these two triangles, right? As you can observe here, we have CD parallel to AB because this CD is obtained by dividing each value on AB with factor of safety. That's why these two lines are parallel, right? And as you can observe from these two diagrams, you can say XFT, this one, and AEB, this one, are similar triangles. So we can use the relation for the similar triangles to obtain the relation between tau A and the endurance limit of the material. Okay, so on doing so, tau A, height of this XFT, and SSY by Fs minus tau M, which is the base of this XFT triangle, and 1 by 2 SE, S dash SE is the height of this triangle AEB, and the base will be SSY minus 1 by 2 S dash SE. Okay, so we have found the relation between tau A and the endurance limit given by S dash SE, right, and the shear yield strength of the material. So this condition is used for the calculation of the permissible stresses that should be given to the material for the failure of that material. Okay, here we are discussing about the spring. That's why the permissible shear stresses developed in the spring material will be tau A and tau M, and this condition is useful for the calculation of tau A and tau M for the safe design of the spring against the fluctuating loadings acting on it. Okay, so every stress value or the fluctuating load should produce a stress which should be less than these two values, tau A and tau M. Then only the spring will be safe from failure. Okay, so here we have another condition for the slope of the line, the load line given by tan theta equals to tau A by tau M. So here you can see in this figure we have the load line. This is the load line which is plotted by the points according to the fluctuating loadings acting on the spring material. Okay, so that's why you can observe we have tan 2 theta equals to tau A by tau M. So this is the condition, the slope of the load line, and this is the very useful condition for the calculation of the permissible shear stresses developed in the springs under the fluctuating loads. Thank you.